Alrighty. So this is rend3's architecture efficient and customizable rendering. I am CW Fitzgerald or Connor, and I am a professional game engine programmer, and I have been doing Rust for about 2 years now, and I help maintain WGPU as well as my various other side project or various other projects such as rend3. There we go. Okay, so what is rend3? Rend3 is a 3D rendering library built on WGPU. It is designed to be very easy to use, but it must be customizable for all of the needs of real applications. So the API is very simple. You create a mesh, you create textures, make materials with those textures, and you put them all together. You create an object that has a mesh and a material and a transform in the world, and then rend3 goes through and renders it using either the goes through and render it. So this is just a sample API. You don't have to look through all of this. This is in our examples, but you can see this is all the code that's required to get a simple cube going on screen from the in terms of like making objects in the rendering world. So it's designed to be easy to use. It has this very simple interface. It needs to be efficient because real people are going to have very complex scenes that they're going to want to render. Big open worlds, very complex complex scenes, and we need to be able to accommodate those. This tool would not be useful is if when it started to scale up, it immediately fell down. In addition, it needs to be customizable. In the real world, when people are making games or making products, the default functionality is almost never going to be enough. There's going to be application-specific problems that need to be solved. The problem with all this is that a lot of these goals are actually sort of go against each other. Being easy to use often means that you omit a lot of the power that comes from customizing. Being efficient means that you have to use optimized data structures and stuff like that, which could make it harder to use or less customizable. So these are basically opposing goals. So we need to strike the balance that is as reasonable as possible using the tools that we have available. So this talk will be discussing how to balance these. As for where rend3 sits in a game engine or in a game's like architecture, you can think of it as just the renderer. For all of the people who use Unity or Unreal just because they have a pretty renderer and then do the rest in a plugin, that's who I'm aiming for. It needs to be easy to get started, and it needs to be easy to use down the line. And I had this in the last slide that you need to be able to ship on this, which is a very different requirement than being able to make something with it. Because it is very easy to get started with a lot of things, but it's very hard to go that last mile and actually make a finished product. This library needs to be able to be used in real production software. It means custom graphics, it needs to scale, and it needs to be predictable. And I don't think people give nearly enough emphasis on that predictability part. You need to be able to look at a piece of code and estimate how that's going to hurt your frame budget. You need to be able to run on a different machine and expect it to work and to know how you expect it to work. So yeah, before I go on any more in the talk, I just want to show off some pretty pictures from some of the users who are using this. This is Animat's Viewer. Animat's Viewer is a viewer for the Second Life world. And so this is the Second Life world. It is loaded in with eh, with no kind of mesh LODing or anything, and it runs well despite how much content is in the world. This is my stress test scene that I use for my example, for my GLTF loading example. It has something on the order of 20 million vertices and 50,000 objects, and it is a very good stress test. And this is I believe I don't remember where this is, but this is again in the Second Life world, showing how transparency works, and you can see through windows, but you can see the decal of the dirt on the door and such stuff like that. All right, so now with the pretty part through, let's take a look at. That's not what that says. We're going to split up this talk into three different parts. These are the three main takeaways I had when building up the abstraction that is rend3. And the three most important things for me are careful scope reduction, having ubiquitous defaults as a means of customizability, and to just optimize your use of data structures. These three things have made rend3 what it is and make it able to achieve its conflicting goals. Part 1, scope reduction. So a 3D rendering library is a very poorly defined construct. There's a lot of different ways you can go with that. And to that extent, there's a lot of experimentation in this space that is possible. And rend3 wants to be able to have people need to use rend3 for more than just rendering. Because people use the GPU for more than just rendering. People use it for simulation. People use it for object selection. You have a massive scene. You want to click on a thing and figure out which object you're clicking on. You can use the GPU for that. But there's so many problems you can solve in this space. If I solved every one of them, I would never release rend3. And that almost happened to me twice. Scope creep is extremely deadly. I know this has been said before, and I just want to emphasize this from my personal experience. It can and it will kill your project if you don't rein it in soon. This example that caused me the most problems is supporting custom shaders. Real games need those custom shaders. I tried multiple different solutions. Every solution was more general than the last. It was more powerful. It was actually calling back to Clark's talk. It was more unopinionated. But by being unopinionated, it meant that my API surface ballooned. And I'm a single person. There's only so much I can do in a day. And I was not able to add any new features because I was trying to do this massive refactor that tried to, do everything. And every single time I made a solution, the user would have to express themselves using my solution. So there is no custom code. They would always give me the thing that has to be done, and I would do it. The problem was this was taking forever. It was getting so out of scope, and it took me 8 months to finally end up at the solution I ended up being at. But those 8 months, all of the momentum rend3 had, and it was building up some, completely died. I am very lucky that I have one or two users who stayed with me through that whole 8 months. They were, thankfully they were doing other stuff on their projects and didn't need rend3 features right now. But I was very lucky. This could have killed my project. This could have eliminated my strongest users. So, the actual problem I was facing was was custom shaders, and my solution to this was a render list. It was a render graph, basically, but without the like auto scheduling. So it's just like a list of like do this, do this, do this, do this. I was trying to encode everything in that list. Like all of the objects you pull, the shaders you use, this, that, and the other thing. And every time I did that, I would need to make it more and more generic because I could think of a solution, a problem that didn't solve. Got more and more, but I wasn't actually thinking about what my problem was. My problem was basically I need to let the user write some of their own code. That's not a very hard problem to solve. I mean, it has its difficulty, but it's fundamentally not that difficult. And I realize I'm using this beautiful abstraction layer, WGPU, that supports well different individual components working together on the GPU. Why am I solving this problem? WGPU already has. I can just give the ability to use WGPU to my users, and that gives them the power they need. Uh, that gives them the power they need to do what they have to do. It was a beautifully simple solution. After this 8-month refactor, I ended up with code that looked so similar to where I started. And for that, I almost killed the entire project. Be very, very wary of scope creep. And most importantly, when you're designing a solution, solve a problem. Like you can't design a solution in search of a problem. The question of, oh, I should solve that is something I've like done numerous times. It's like, oh, I might as well solve that. But why? That's just making my library bigger, more complex, and need to solve more problems. It's more code I have to maintain, and it's more complexity the user has to deal with when figuring out how to use my library. Know your problem parameters, and know that you have a problem. Don't solve a hypothetical problem. And when you see this hypothetical problem, waiting to solve it won't kill your project. Solving it might. All right, so now we're on to my preferred way of giving customizability to users, which is ubiquitous defaults. Whenever you're doing anything complicated, you need the ability to customize. There's some default behavior that most people will need, but some people need something different. One way to solve that is just give a whole bunch of options. 100 options, whatever. And when you give that to a user has analysis paralysis and shuts down and uses a different library. Because there's so much complexity. They don't know how to make decisions about every single option. But for the most part, there's a good default. You probably want this. And that's where people should start. So and in a lot of these situations, the options aren't really needed too. So you don't want to burden every single person who is using your library from having to figure out all of these problems when they don't really have to. Again, calling back to Quark's talk, this is how if you're just foisting the problem on the users, it's still your problem. This is one way to solve that problem is to provide defaults. Model common solutions, and by having helpers as opposed to intrinsic functionality, you move the code into user space, which means the user can change it. That is really helpful. So here's a very simple example. Rend3 needs to be able to use WGPU instances, adapters, devices that are provided by the user. Sometimes someone is making a project, they are using Rend3 alone, and they don't have any of this already. But some I'm integrating into an existing WGPU project. Maybe they want to add 3D functionality in this one particular place. We need the ability. The user we need the rend3 needs the ability to use custom devices, adapters, queues, whatever. But the user shouldn't have to go through the adapter selection process. The adapter selection process is not complicated, but it's like 100 lines of code. It's a bunch of like kind of finicky for loops to like figure out, oh, is this one better? Is this one better? Like you have to sort the adapters. Like it's a whole nasty thing. But you must be able to customize them separately. So we move this problem into user space. We provide a function that is simple, that you just say, oh, I want this backend, I want this backend, I want this device, I want this renderer mode, or none of them. Just have it choose for you, and then just give me back the thing I need. And by doing this, the simple case is very easy, and the complex case of a user providing either their own adapter selection logic or providing their own adapter at all is solved. So we have the options, and then we have the default. More complex example, the solution I had to the problem of customized rendering is something called a render routine, which is what I described before. It is a section of WGPU code that takes the input provided by rend3's like data management system and renders that. Now, every user of rend3 shouldn't need to write their own renderer. That's kind of defeats the entire point. But they also need to add their own. They need to, do crazy effects whenever, like, I don't know, the explosion happens. So they need to be able to customize that, but they need a default. So we provide a default for the same default case, which is physically based rendering. So we provide a PBR render routine that you can just drop in and use, using it as like 4 lines of code. And each of that render routine is composed of small composable parts. If you want to do PBR differently, you don't have to redo everything. You have to take the high-level render list and recompose those individual parts and change the little tiny bits that you want to change. Everything else can remain the same. There will be some coming in the future. There will be even easier to reuse parts, but I'm not going to talk about that because I haven't quite solved that problem yet. But it is very possible to do this today. All right, and now this is the biggest part of this talk, which is optimization work that I did in rend3, actually last weekend. So this is all going to be talking about optimizing this scene in particular. There is 50,000 objects, 20 million verts, rendered on a fairly beefy computer. Took 16 milliseconds on the CPU and 15 milliseconds on the GPU. We're only going to be talking about CPU today. GPU, perhaps if there's another GFX talk, will be in that one. So this scene is rendered to 4 different cameras. Actually, sorry, that's wrong. There's 3 different cameras. There's the main camera and then 2 shadow cameras. But that means that because we have a depth tree pass, we have to render 200,000 objects per frame. And we currently do that in those time frames. So today we're going to be working on making that 16 millisecond mark lower, as personally I wasn't terribly happy with 60 FPS at 5,000 objects being the sort of CPU side limit. So let's talk about performance requirements. This is the CPU side loop. This image is Tracy. It's a very, very useful piece of software. You add spans into your code using either the Tracy library or the profiling. The crate's called profiling abstraction, which allows things like WGPU to have their own spans but not tie themselves to Tracy. Tracy is very, very, very useful program. And we will be using it to dissect how long things are taking. And we're just going to go down CPU side because GPU side is a lot more complicated and it involves a lot more tricks, but it's still very possible. We will get that 60 millisecond number down. All right, so I mentioned this before. This is a very clear overview of rend3's object system. So objects have materials, materials have textures, and an object also has a mesh. Important things. Uh, materials are render routine specific because the only thing that the only thing that needs to know what a material is the shader that's rendering it. So there's a clear tie between the material and the thing. And if we want custom shaders, we also need custom materials because that shader may need who knows what kind of data for that object. So we just need to be able to store a set of textures and a set of data. And we need to store objects that could be pointing to any different material. And we need to be able to change which material any object is pointing to. And we need to handle that all transparently. And we need to do it efficiently. Oops. So how do we do this? We define an ABI for a material. We say that a material is some textures and some data. That's it. We don't care anymore. WGPU actually doesn't care anymore. That is the limit that I need to know in order to get this data onto the GPU and into your shaders. So this is a very convenient model for how materials work and allows them to be fully generic. So how do we store this? We have a bunch of handles of materials, and we have a bunch of materials that could be of any concrete type. Very simple solution. We take a hash map, have a handle, and then we box a Dyn material. Boom, done. There's a couple problems. There's more than a couple problems. Number one, the idea of you can't say, "Oh, give me all of the materials that are this." It would require iterating over the whole array. It takes a long time. Every single time we access a material, we eat a cache miss because we're chasing that pointer, chasing the box, which is a pointer, and we have to what is it called? You downcast. That's the word. You have to downcast to the concrete material, which is not expensive, but it's not cheap either. So how do we fix this? And we draw inspiration from the ECS people because that's the same problem. They have a set of entities that are storing arbitrary data, and they're storing arbitrary data. Each one is different, but fundamentally, this is the same problem. So we steal their solution, archetypes, and we can just store all of the same type together. So instead of having a map, instead of storing a box of Dyn material, we're storing a box of Dyn any, and that any happens to be a vector. And we know that a vector of the underlying type. So if we say have a PBR material, we will have that archetype map will have the type ID of the material going to a box that is pointing to a vector of that material. So that way, when we're iterating through all of the materials, we just have to eat that dereference twice because we have to dereference first the box and then the vector, and we get to iterate them through linearly with a single deref or downcast. Sorry, very efficient, very good. We now have to do some handle lookup to be able to say if we wanted to say I want X material, we have to first figure out which type it is, and then figure out which, and then actually go in and access the thing. But this is not too bad. This is not too bad. We can do better though. I don't know if she's in the audience. I saw her on the on the Discord. But big shout out to Violet, for her work on the list any crate, which basically flattens a box of a vector. Because the vector already has the indirection, you can actually store the the polymorphism inside like that pointer. Very smart. It's a bunch of unsafe code that I'm very glad I don't have to write, and it works wonderfully. I highly recommend if you have this problem, go use it. So now we don't have that double indirection. This is looking very clean. All right. So how do we access objects? How do we actually determine which objects we need to do stuff with? And a render routine needs to query for the objects it cares about. It cares about that object if it has a material that they know what to do with. You know, generally speaking, one material ties to one shader, so they have to query separately all of the things with one type, all of the things with the next type, all of the things with the next type. But there's also an extra layer there. Sometimes shaders, it's not a 1-to-1 ratio between materials and shaders, it's 1-to-many. There are some properties of materials that require switching shaders, or switching pipelines, or switching some sort of concrete state. And this is, we add what I call a object key. So a material will say, hey, here's a U64. If this U64 is different, this should be considered basically separate. Not a separate material per se, but in its different archetype. So, we don't need this for certain properties of the material. Transparency. This is the one it came up in. I need to be able to say, give me all the opaques, render it with this pipeline. Give me all the cutout objects, render it with this other pipeline. Give me the blend mode transparency, render it with this pipeline. So this is the old way of doing it. This is before we started making materials generic. Iterate over every object, check to see if the material type is correct, and if so, check the properties of the material. This is really slow. Because, say, you want to query for the one explosion. You have to iterate through all 50,000 objects every time. Say you have, I don't know, 20 different shaders. You now have to iterate through those 50,000 objects 20 times. That is horrendous. We can do better. What if we store objects archetypically too, with the material type and the material data as the key? Now we can query, say, I want every object that has this material and has this data. And it just gives you back a list. It doesn't have to iterate through anything. Boom, you have a list. Yes, if you want to deal with more than one at a time, so you want to deal with two different transparency modes at a time, you have to do 2 queries. But queries are now extremely cheap. So this works really well. Once we archetype things are looking better. We have 50,000 objects. Our CPU time went from 15 milliseconds to 10. We're doing good. There's a lot still on the table. Building input data, taking up a lot of time in this thing. Remember, 50,000 objects is not enough. So being satisfied at 10 milliseconds is not enough. And remember, I'm running this on a very powerful machine. People are going to run this on machines that aren't this and have problems. I want to be able to support this in as many places as possible. This is a silly one. This is one you really have to look out for. When I'm building my object data, I create a vector, I pre-allocate its space, and then fill out, and then put data into the vector. The problem is, I, in this line, said, oh, I'm going to multiply the amount of objects by the size of because this is a byte array, the amount of objects times the size of the struct I'm storing in them. But I have a header. I have a header file in there. Not a header file. I have a header bit of data. Which means when it got to the very last object, it forced a reallocation of this 5 megabyte vector, which if that realloc failed, you're going to eat a mem copy. This is terrible. By adding the uniform size, boom, that reallocation completely disappears. Really silly, shouldn't have ever happened, but that kind of thing can actually hurt. Because of this reallocation, we went from 10 milliseconds to 7. That's a 2 times speed up from the original. Our mem copy inside building input data is running around 6 gigabytes per second. It's fine. We can do better. Theoretical limit for mem copy is somewhere between 15 and 25 gigabytes per second. Improving our mem copy. If we look in here, we have a single line which is a material internal index lookup. This, as we covered before, is basically a hash map lookup or 2. I think it was actually 1. This hash map lookup is a problem. Like, we're spending a decent amount of time doing this lookup. How can we fix this? We need a raw index, but we have this handle. Handles are designed to be stable, but indices aren't. Because, like, you shuffle things around in the vector. We have a tight loop iterating through that lookup every single time for 50,000 objects hurts. But what happens if we store the index instead of the handle? This is referred to in the database world as data denormalization. We're pulling data from one place and storing it in another place for the purposes of quicker lookup. In exchange, we have to, whenever we update that value, we need to now go change it everywhere. Means every material has to have a handle back to its object, which is fine. This is a very rare case. Materials don't change that much. But we have to iterate through every single object all the time. So, yes, material changes don't happen very often. This loop is iterating 20,000 times per frame. So, pessimizes material operations, but optimizes this mem copy. That's what we're optimizing. Removing this hash map brings us down to 6.3 milliseconds. We're now at 2.4 times the original. There is still more on the table here. 6.3 is not that different from 7. We need to get those mem copy numbers up. I was going to have a slide that showed the assembly that was going on, but I tried to pull that up this morning and my computer blue screened. So you get this lovely X. You're going to have to trust me on this, that in this assembly, there was a lot of shuffling going on. And all this shuffling was just taking a long time. Like, it had to do small reads and small writes. If you know anything about like how CPUs work, it's very good if you can do like big writes and big reads, and that's the only way you can actually get performance. We need to stop shuffling so much. Look at these two structs. Look innocuous. We build the right struct from the left. We just like steal the transform, steal the sphere, steal the various like integers. Problem. We have to shuffle them in memory. Like, they're in different locations in the struct. So we need to have to load that U32 individually and put it somewhere particular. We can't do any kind of bulk copies. These are aligned 16 Reaper C structs. So the order you see is the order you get. It was so simple. You put one struct inside the other, and you're done. Now we can copy that whole struct all at once. That's a single massive, not massive, these structs aren't that large, but like one single mem copy. Trust me when I say it, this code was literally 4 16-byte reads, 4 16-byte writes, just in a loop. It was beautiful. This was like music to my eyes. Yes. All right, we also have another mem copy in here. We're using a very useful helper function called create buffer init, and it basically you give it a slice, and it just makes a buffer with that data in it. It's very useful. Highly recommend it. But we're talking about a lot of data. We're optimizing here. We're creating a vector, and then we're copying it inside this internal thing. Copy doesn't matter for small and infrequent data. If you're uploading 64 bytes, just use create buffer init. But we're uploading 5 megabytes a frame. WGPU and WebGPU, by extension, offers a mapped at creation, which is actually what create buffer init does internally. It allows you to get a pointer to this staging buffer. And so let's just make a buffer and get the pointer to the staging buffer and write the data in there as is. We know the count already. After both of these optimizations, we're hitting 2.8 milliseconds. Our memcopy routine is running at 20 gigabytes per second, and we're at 5.5 times the original. We're doing very well. This is like, we could say we're done here. I'm not done. Notice something. We are building up the input data. This scene, for reference, is basically all opaque objects. So these massive build input data is building the input data for the opaque. There is in there the building input data for transparency and cutout materials, but we're basically ignoring them because the count is low enough that it doesn't matter. There's 1,000 cutout objects versus 50,000 opaque ones. Let's see. Okay, let's not forget the dumb stuff. This is a lot of this talk, so like, don't forget the dumb stuff. We're doing a calculation multiple times. We're building and uploading this culling input, and we're doing it 3 times. But we have to cull for every single camera because there's 3 cameras. Because every camera, the shadow culling will be different from the, main camera culling, stuff like that. We have to cull it differently. We don't have to build the input differently. The input's the same. We're doing 3 times the work for no reason. So I stopped doing that. We're at 2 milliseconds now. This is where we're stopped. 7.8 times the original. Very, very happy with the results. As you can see, there was just a single building input data. When I first tested this, the number I got was 1.7 milliseconds, which would have been a lot more satisfying, but I actually redid all of these tests and made sure I got a representative number, not just like the best number. So we're only at 7.8 times the original as opposed to 9, which makes me sad because 9 was almost 10. I was so close. But there are ways forward. We could not build buffers every time. We could, now run render pass inside of WGPU is a good chunk of my time. So, submitting all of these things could be optimized, but these would require a significant amount of work. And now our CPU loop, total end to end, outside of just this render loop, is 2.5 milliseconds. Our GPU is still running at 15 milliseconds. We need to fix that first. But that's for another day. What do we learn? Profile everything. All the things that I thought would be slow, making buffers, making a bind group multiple bind groups every frame, doesn't matter. Absolutely does not matter. You could, they're in there, but they're what, 100 microseconds? Who cares? All the things you initially thought were slow weren't. So, profile. You don't know what's slow until you look. You cannot predict the performance of computers. They're too complicated. There's another lesson here that is sort of that is weird. I could have solved this problem with threading. This is a threadable problem. I could have thrown those onto threads. I would have gotten my frame time down to 3 milliseconds because I just did everything in parallel. But I'm not solving the problem. I'm just paper overing it with hardware. This is not what we want to do, especially if we want to scale. Now I'm in the location where I have now optimized the living bejesus out of all of this. And when we scale up really, really far, now we can pull out threading and we can get truly amazing numbers out of this. In addition, we could have solved this problem with sparse updates. We're updating every object every single frame. And yes, you can do sparse updates. It's a lot of work. It's a lot of shader code. GPUs really don't like sparse things. They like dense data. And this didn't require massive architecture changes to allow all of the shader code and all of this to do sparse updates. So, if you take away anything from it, hook up a profiler. When you're optimizing, look at real data. Anything else does not matter. And this is my personal opinion, try and avoid threading until you have exhausted most other options. You will be surprised how far you can get. All right. And finally, the last part 4 of the 3-part talk is conclusion and the future. I have already gone a little over time. CPU has been tackled. The GPU is next. This is a picture of Radeon GPU Profiler, which is a AMD profiling tool. And you can see that the GPU is doing a whole lot of nothing. The green thing is a bunch of vertices. It's like doing vertex computation. But because this is rendering 80 million polygons per frame. Sorry, 80 million vertices per frame. It's just trying to render all of those vertices. And it's just slow. But we can fix this. But that's not for now. Maybe next graphics meetup, if that's a thing. All right, I am going to release rend3 0.2 very soon. We have this new material and object system. We have all of these optimizations, and we have the ability to do texture uploads in a multi-threaded fashion that allows you to do the CPU side work of texture uploads more in the other threads. If you want details on that, come find me later. It's complicated. And then for 0.3, coming composable render routines, eGUI and ImGUI integrations, and all of these juicy GPU side optimizations. 0.2 release coming soon. I'm aiming for a 1-month release cadence correlating with the meetup and the newsletter. Finally, acknowledgements. Thank you for all of my contributors. Scooper, Noxum, and Mindswipe. Quark, thank you, besides for everything, for ideas about how to use ECS patterns inside of a renderer. And thank you, of course, to John Nagel for testing, support, spearheading ideas, giving me screenshots. He is a real one. Finally, we have tons of stuff to do. Come help us. Feedback, contribution, ideas, all welcome. Something doesn't work, let me know. Here are a bunch of links. These links will all be in the uploaded slides when we upload them into the GitHub repo. And you can just find me either on the WGPU Random Discord or WGPU Random Matrix, and as my username on Discord. And that is it. Thank you for listening to me spiel about my project for 45 minutes.
Hey, thanks, Connor. That was amazing. I would say it escalated quickly to the performance section, which everyone was shocked to see. I was curious, all of the talk was like, oh, he's running on a beefy computer, so he must be using like 32 threads to record this in parallel. And then I saw this Tracy screenshot you have, which is just saying main thread. Like, it's not possible. We have the benchmark with WGPU HAL that like renders 50,000 bunnies. And this guy renders a whole lot of a scene instead of bunnies, and it runs faster. What's
It,
going
it
on?
it really helps when you have 3 draw calls. That
Right.
is 3 multi-draw indirects just firing off the whole scene. It's beautiful. I also have a mode that doesn't use multi-draw indirect for things like older machines or DirectX 11 or whatever, and that is currently running at 60 milliseconds per frame on a single thread. So that's more of what you'd expect. But 60 milliseconds versus 1.5 or sorry 2.
Mhm.
Sorry, I couldn't quite get to 1.
Yeah, the numbers are crazy, just crazy. I'm super pumped. Thank you for sharing them. So we have a lot of questions. I'll try to go through them quickly. One, I'll start with mine. So this is the renderer, and it comes with its own ECS, right? Is the ECS an implementation detail of rend3?
Absolutely. So
Okay,
I'm
so
actually not using a proper ECS. I completely like rolled for this implementation data store that steals a lot of ideas from ECS. So from the user's perspective, you're still just like adding a material and adding an object. The fact that that is stored inside this complex data structure completely the user has no idea, which is the whole point. Is can we get this performance? Can we get this customizability without sacrificing this interface?
right. So if I'm writing a Unity engine, I can still expose my users to some ECS, and that would be compatible with rend3.
Yes. Yep.
Yeah, awesome. Next, a bit of a tricky question. So you represent materials as the raw data for constants with the bunch of textures.
Yes.
Um, how would I go about the buffer data if I need it, if it's not about constants? Like I need a storage buffer with a whole lot of statistics from somewhere.
So
Is
storage buffers, stuff like that, that would all be inside the render list. So this would be, for example, you could upload a storage buffer with all of the whatever data you have, and then store in the material an index into that buffer. And then when you're writing your render routine for your shaders, you will say, give me all the objects with this specialized material, and then you just iterate when you draw them. You look up inside this buffer and figure out whatever data you need. So that's the whole point of having render routines be just arbitrary WGPU code. You can
Mhm.
add whatever you want.
Oh, great, great. Um, and your API is retained, if I understand correctly. Like
Yes.
you push objects to the scene, and they are kept in the scene until something happens to them.
Yep. Everything is
Okay.
retained. All of the handles are ref counted. So things will be, as long as you have a handle open to it, it will stay alive.
Mhm. And a question from the chat: did you consider using an existing ECS system?
I thought about it, but because of how much of this work has to go on the GPU, and I have such strict performance requirements, um, and I'm not quite an ECS. An ECS is mainly for the case of entities have n components. I'm a special case of that, where every entity, i.e., a material, has exactly one component, and I can optimize because of that. So
Mhm.
I thought about using something like Hex, or that's all I would use. I would use Hex, but I needed to be able to get at the raw data, and having that raw data already there is very helpful.
Awesome. Next question from Forrest. What are the benefits or maybe clear disadvantages of going with WGPU for rend3? And remember, this is not a conference about WGPU, so you can put any criticisms you need.
So I mean, I have nothing but praise, but the big thing that WGPU buys me is, number one, I don't have to deal with the problem of barriers. Because, like, most render graph implementations are basically barrier generation. And yeah, there's some like resource allocation and stuff like that. But for the most part, it's just trying to like schedule and barrier things. And that's completely WGPU's job. I have an interface where I can just do stuff. There's no implicit state. In Vulkan, you have to know what the state of the object was before, so you can correctly transition it. You have to know if it needs transition at all. All of those things would leak into this interface. Whereas with WGPU, I just say, I want to use this, and that's it, I'm done. They're all going to be, of course, performance overhead. But being frank, I probably can't do that much better than WGPU can. I still have to build up all those abstractions for auto-generating barriers and stuff like that. And if I'm going to do all that, why wouldn't I just pour all that effort into WGPU's barrier system? Or optimizing WGPU. And that way, all the work I do helps everyone else too. The only way I'm basically of the opinion the only way you can write a sane Vulkan render is if you have 100 people doing it. And the only way we as an open source community are going to do it is if we do it, if we focus on one project and make that one project, put all of our effort into that one project so that we have that 100 people. And once WGPU had all of the GPU side features I needed, multi-draw and direct, I don't yet have like subgroup ops, but that's not going to be hard to add. All of those things. Once I knew I could do it, there was very little reason to use anything else. The only other thing I would consider using was DirectX 11, and that doesn't do what I need. So.
Mm-hmm. Right. It's amazing how much synergy there is between our talks, which is accidental.
Yeah,
A lot of topics are just similar.
Yeah, I didn't expect that. That was a very pleasant surprise.
All right, a few more. Did you split the scene that you benchmarked? Split it up. So the question is, if it was a single mesh, obviously you would just do a single one instance draw call. But depending on how you split it, it's very relevant to the optimization. So how is it split?
It is split exactly how Unity split it. I exported this from Unity, I turned it into a GLTF. It turns out it is 50,000 objects in the scene. That could, because I'm bindless and you can have more than one material per object, I totally could have, uh, made it all one object and just rendered it all at once, and that would have solved this problem too. But my use case, the game I'm supposed to be making this for, has the worst case scenario for this. It has a bunch of objects that have 4 verts, because everything is just a bunch of planes, and maybe there's a cone or something. So you have tons and tons of objects with different textures, all over the place. Which is why I went bindless. Which is why I went multi-draw and direct, because now I can deal with 100,000 objects on screen and deal with the fact that every single one has a different texture. Without that, if I just merged everything, I wouldn't be able to support that use case.
Mm-hmm. And a similar question is, did you consider merging any of the static objects?
That would basically be the user's problem, because I can't guarantee that merging static objects is universally going to be correct. Because even if you have the same texture, there's a whole bunch of scenarios in there that things could be just subtly wrong. And what happens when you move one of them? I'd have to unmerge and remerge. So I don't have enough information there to do that. So that's on the user. And because of that, I'm just faithfully rendering this GLTF. I was very happy. I took this GLTF, I put it in the 3D viewer of Windows, and it got about 1 frame per second. And then I was like, "Ooh, I'm at 60! Yay!"
Another question. The premature optimization is bad. At what point did you start thinking about optimization?
once I had a concrete benchmark that worked. So basically, I have this scene, and I was, for a while, just trying to make things work again. Shadows had issues. There was some culling issues. There was that barrier problem that was causing shadows to spaz out. So it was only once I actually got to the point where the thing worked, then I took that into a profiler and figured out what was going on. Because I knew that I wanted more. I just wanted to see if there was more I could do. And I was like, hey, look, there's a place, there's a place, there's a place. Let me give that a weekend's worth of work. And this is what became of it. And so these all turned out to be low hanging fruit, basically. It was not a small change, but it, in the scheme of things.
Mhm. Thank you. Another question: um, are can you can define your materials in the code? Can you also try to define them with data?
Sure. Um, the one thing that would affect, the one thing that would affect that is that you have to know the material count at compile time. This is not the material count, the texture and data count, which is actually probably something we could do away with. But there is the implied knowledge that every material in the type has the same length. So there is probably some evolution of this API that could improve that use case. And if you have that problem, file an issue. Let's talk about it. I'd love to figure out if there's a solution that could work for that.
Cool. And the last question, I'm not sure we can answer that in time. The question is, what is the new material system? What's the design for it?
So the materials didn't change. The PBR material is identical, but now it's the rend3 core doesn't know about the material. It just knows about the material interface. So the rend3 PBR render routine knows about the material, but that means that you can come in, write your own render routine, write some funky material for it, and use that inside of rend3 while you're using the PBR one. And so that allows more customization where there otherwise wouldn't be.
Right, that makes sense. I think we'll need to wrap it up because we're running short of time. Thank you, a round of applause for Connor. It was amazing. And we still have one very important talk in front of us from Andreas. So let's switch to that.